Hello everyone, my name is JIAXIANG, aka FXTI. My GSoC project is SLEIGH Disassembler Backend. It's a bridge from SLEIGH to Reader 2. About me, my nickname is FXTI, and you can find me on GitHub and Telegram. I just finished my third year computer science majoring in China University of Mining and Technology. I have refactored Python bytecode plugin and a big number module in Reader 2. I like compilers and decompilers. About R2 GZHOU. Its release in last year. It employs GZHOU's underlying decompiler. This decompiler is 100% written in C++. So this project reuses this reader to reuse this decompiler and communicate with it in XML form. That is the core idea of the R2 GZHOU. Let's take a closer look at the decompiler of GZHOU. First, it contains the SLEIGH engine. It's the main disassembler used in GZHOU. It will read a bunch of specs, like the processor spec and the compiler spec and dwarf and more. This spec is associated with one certain architecture, like the ARM, MIPS. When load the binary files, SLEIGH engine will read in these specs and be ready to parse the row instruction read from the binary, and the SLEIGH engine will then use those rules to translate the row instruction into the P code. And the P code is GZHOU's immediate representation, also aka IR. Those IR will be put into the further process, like the control flow instruction and the functions recovery and the further decompiler process. So what do we want? We want to reuse this SLEIGH engine. We want to read its P code, and on top of that, implement our own disassembler and analyze plugin. We will not only want to get the instruction disassembler result, but also get us the control flow info and the emulation work. But why? Why do we choose GZHOU's SLEIGH? First, it supports so many architectures. If we can just reuse this engine, we will only need to write the associated RBIN plugin, and SLEIGH will take the rest of the work from here. Actually, I think the P code it generated is quite good. Actually, it's quite usable. So this is the motivation of carrying out this project. And first, let's talk about the disassemble part. This part is relatively easy. I need to dive into the spec file parsing process and export all interface we need. We will need the info like the registers of this architecture, and we will need the low-level disassemble interface. Also, we will have to properly initialize the related data structure and set those flags to make it work. But it's easy. And here's the result. You can see that those instructions are properly disassembled. But when things come to the analyze part, it becomes much harder. There are three main problems, like extract control flow from the P code, and how to identify the type of the instruction. And the third is how to translate P code into ESIL. ESIL is reader's IR. Is used to mainly for the emulation work. First, we will need to extract control flow from the P code, and actually there's existing API can help us do the work. It's called SLEIGH instruction prototype, but it's implemented in Java code base. And for the C++ code base, we will only have function level analysis, like the flow info. But Java code base have both the instruction level and the function level. So what can we do? We will have to port the SLEIGH instruction prototype from Java to C++. It looks easy, but however, Java and P code generation process is they looks like each other, but there's still difference. And to do the port work, you will have to touch the internal data field and some protected or even private method. So to minimize the changes on the GSoC source code is the biggest challenge, and you will have to read through all the related codes. And I'm proud to say that I managed to do it in just 2 lines of changes. I only need to export 2 private fields, and I can successfully port the SLEIGH instruction prototype and manage to extract the control flow from the P code. And here is the result. You can see that the control flow is properly drawn, means the control flow info is correctly extracted. And we will have to identify the type of the instruction. You can see that this instruction is just arithmetic redshift, but SLEIGH generated more than 10 P code for it. So how can we just identify the type of the instruction to know that it's redshift from so many P codes? To do this, we will have a good knowledge of the type of the instruction. So I do an overview on the OP type that reader supported, and by checking the various case of the P code generated from the original instruction, I will summarize the pattern of this type. They are common traits, and write out the pattern, and implement these APIs to identify the type based on the pattern. And here's totally 12 kinds. This is the final result. But it doesn't explain how we actually work, so I prepare an example. And this instruction is absolutely a push. So the key P code is the last one. Is to store something and into a memory space, and its address is specified by RSP, and the value to put into these places is a unique var node. And in GDRA, something in the unique space is actually, you can see it as the temporary variables, like these two added and give out and temporary variables, and it will be used in the further calculation. So just keep that in mind. And for this store, its output is absolutely RSP, and since its space is RAM, so you know it's a memory reference. And above this input is a temporary variable, so we have to look up. And for this, it's copied from another unique var node, so you just look up again. And now you know it's read from memory, and its space is also so let's just look up. And now we know that it's RCX register and plus this immediate value. So we know the input is first it's a memory reference. Its size should be 8 bytes, and the basic register it should be RCX, and the offset should be this immediate value. So we successfully resolved this OP's input and output, and we know its type should be push. And we do this for 12 types, and who match the first is the final result. And this is the core idea. And here's the result. You can see like the push and the core move. They are all correctly recognized, and this is the debug display. You can see that the inputs and the destination are correctly resolved. And things come to the final part, how to translate P code into ESL. First, let's take some example. Like this P code, we want to copy linx1 to a unique var node, so it's middle variables, and just ignore this equal. It's type it a mistake, so it should be just 1, and this value will stay on the stack, and it's intentionally. I will explain this later. And let's check this result. Check this example. It perform an AND operation on the EAX and 1, and store this result in a unique var node. So first 1, and second we push the EAX, and we call the get command. This is a custom command. It will get the actual value from EAX, so it should be 1, and the value of the EAX, and perform an operation, and the result will stay on the stack. Right now you have the first look of the translation. So I will state the problem. When register is just 1 R, like an A, it will be treated as a value when you doing the compare. So you will have to bypass this case. And the second, flow register need a unique interface to fetch the value onto the stack, because current ESL doesn't support float arithmetic. There's just integer operation. So if you push a float register on the stack, the value fetch work will not be properly performed. You will have to do it by yourself. Second, if I choose to leave the middle variables on stack, how to fetch them? The current version of ESL don't have pick command. There's just a swap, so you can only reach the last two the two stack top variables. You will have to bypass that and add your own pick. So the solution is here. First, add get to push register onto the stack, and get and also properly handle if it's integer register or if it's float register, and fetch the value properly. Second, it's a rule. All elements on ESL stack involved in calculation will be prefetched. So the only pure value will be on stack waiting for operation. This will work as a guarantee that all value involved in the calculation are pure value. You will not worry about the register read or register read problem. And third, add pick command to fetch element on the stack in random access. Now with this command, you can access any middle variables just you left on the stack, and this will make it fully emulate the P code's work. And fourth, override equal to store value from stack back to register. This is too compatible with the float number, and the next to override is also too compatible with the float number, or the actually number be written or be read will be performed with the integer operation, and that's wrong. And finally, add a series of float operation like the general plus, minus, multiple, and division. And with this all done, you will have a ESL that supports the P code. And here's the result. Here is the SAR's P code. So many, and you can successfully translate them into the ESL. Although it's long, but they are equivalent. They will have the same side effects, and that's perfect. Now I will show you some demo. Wait a sec. Okay. Now you can see it. Let's first start reading, and we're gonna test the case. And to use this plugin, you should use the command pdga. This will switch to the you can see the help. This will switch to the RSM and RAnalyze plugin driven by SLEIGH from ZHOU. And now use the AAA command. It will successfully parse it. And let's see the PD results. No problem. And what about the VVV? Let's do that on different function. Yeah. This all work normally. And now it's merged into the main string and it's ready for you. You can just test it and enjoy it. Hope you will like it. And now, and finally, I want to thank my mentors. They helped me a lot on the development process. Without them, I don't know. Just express my gratitude, thank them. And I'm ready to do the question. Any problem?